Hello and welcome to another video. In this video we're going to be doing the premium weekly problem for this week, and it's going to be implement try 2. So a try is a prefix tree. I actually wondered if you pronounce try, or tree. Now I guess I know. So it's a prefix tree that's a data structure used to efficiently store and retrieve keys in data set of strings. There's various applications such as autocomplete or spell checker, and you want to implement it. And so you have a try that initializes it, you have insert that inserts the word, then you want to have the count words equal to, which returns the number of instances of string word in the try, and then you want to do the same thing with words starting with that word. So it has that as a prefix. And then you also have erase, which erases the word from the try. So let's briefly talk about the difference between prefix and start and equal to. So I'm assuming you did like the first try problem, and if you didn't, I think I have a video for it, and I have a recent TypeScript one. So definitely you should be familiar with just like how to make a normal try. But I will briefly talk about like what things the try has, right? So try, the old try had usually, like for most LeetCode problems, it has a children dictionary where the key is a letter and the value is another try that is just like traversing deeper into that one. And then it also has like a Boolean is word, meaning like, is this try the end of a word or not? So the difference between count words equal to and count words starting with is like in the first try, it asks, did this try instead of having a count, it just said like, is this try a word and is this try a prefix? So let's just briefly look into like the difference there. So let's say I'm just going to draw tries as nodes and then a path as a letter. So let's say we have this like root try here, and let's just say we have an easy word like ball or something. So essentially it's going to look something like this. B is going to make a new try. A is going to make a new try. L is going to make a new try. L is going to make a new try, right? So this would be like the root, and then these are all keys in the children dictionary that make new tries. So this L is a word because this ends the word ball, but this, like anything here isn't a word if we just inserted ball because it's not the end of a word, but it is a prefix. So there are words that start here. So all these are prefixes, but the only word that's a word is this. And so it's going to be the same thing for the count. We can just, instead of having a word Boolean, we can just have a word integer that will just be 0, right? And so anytime we insert a word, whenever we get to the end of the word, we can just say, okay, whatever try we're in, let's take its word count and let's add 1. And similarly for prefixes, we can also have it as integer. And whenever we are inserting a word, any try we pass through, we will just increment the count by 1. Right? So that's also pretty straightforward. And that's kind of what we're going to be doing. So now there is this erase. And let's actually look through these examples. Let's actually look through this first example. So in this example 1, let's kind of walk through it and kind of try to figure out what's going on. So we are inserting apple first. So let's do that. So let's just have like a root try again, and let's just insert apple. So A, another try, P, another try, P, another try, L, another try here, and E. And so for all of these words, like once we insert apple here, all of these words will have a prefix count of 1, 1, 1, 1, 1, and then let's just say the prefix count is blue, and then the word count here, let's make this brown, is going to be 1 for just the word that ends the apple. Right? So if we insert apple again, then it's going to be the same thing. All of these will just double, right? So A, P, P, L, E. So we're inserting apple again, and now this will end 2 words. So that's what's going to look like there. Now count words equal to apple, there are 2 instances. So essentially, to count words equal to, you will just traverse down apple, and then you'll get to the final try, and you'll see like, okay, how many words are in there? And that's going to be 2. Now count words starting with app. So we would traverse down app, which would we'd go down here, down here, down here. We would be at this try here. And there are 2 prefixes here. So we would return 2. and then try erase apple. And so here, there's a few ways you can do this, and I'm going to do the way that actually will actually delete things when there are no prefixes. But you can just modify the prefixes on the words and not actually delete keys, and that would work as well. So when we erase apple, essentially what's going to happen is we're going to go down apple, and every prefix we run into, we will decrement by 1. So we'll like go down here, decrement this. Everything we go down, we're going to decrement. So this is going to be decremented, and then finally we end up here, and this will be decremented like this. And then what is that? Okay, count words equal to apple, so we're going to get 1 here, and then count words starting with app, we would return 1. And now, so like I said here, when this erase here, you can just modify these and not delete keys. But what I'm instead going to do is I'm just going to say, so let's say we're deleting this apple. I'm just going to go down to this try, right? And I'm going to make this is going to be 0. And then I'm going to say, if the prefix count for a word is 0, that means everything below it needs to be deleted, right? Because, like, you can just figure it out. You can try a bunch of examples, but essentially, if the prefix count for any try drops to 0, then that means everything below it will also drop to 0. So instead of traversing all the way down, I'm just going to say anytime I traverse and a prefix count becomes 0, I'm just going to take whatever node that came from, in this case this node, and I'm just going to delete that key from the hash map. So I'm just going to delete A from this node's hash map. So now this, essentially this path is deleted, which means all of this is just garbage collected, right? Like we're not using any of this now. And so that's what I'm going to do, but another valid solution is just traverse all the way down and just change all the values to 0. But the actual problem with that, as you can see, is if you insert a bunch of words, like let's say I insert like apple, say insert apple, ball, hat, whatever, right? What's going to happen is these keys will still remain, but they'll just have value 0. So you'll just have a bunch of empty nodes that you're not really deleting, but it will still work for like this solution. Because if it'll try to count words equal to apple, these keys will still exist, but because the values will all be 0, all of these will still return the right thing. But instead of that, what I'm going to be doing is I'm just going to be deleting. So anytime we hit a try that has a prefix count of 0, it means all of its children, should just be deleted because this should not be visited anymore, essentially. So we're going to do like a little short circuiting here. To do that. And when we traverse, we're going to keep track of the node and like its child, just to make sure that we can like delete that key in the dictionary. And I'm going to kind of show you how that works. But all the rest of the code is going to be very similar to the try one, but instead of prefix Boolean, we're going to have prefix number, and word Boolean, we're going to have word number. Everything else is all the same. Okay, so let's code that up now. So for init, we're going to have, right, so we're going to have prefixes equals 0, words 0, and self.children is just going to be an empty dictionary. Okay, so to insert is going to be very similar to try number 1. We will just be, starting at the root, and then we will go all the way down, right? So we're going to say root or node equals this, or self, I guess, because Python. Node equals self, then we will just go down the characters, right? So for character in word, if character not in node.children, then we will need to make it. So node.children character equals another try. Now we traverse down into it, right? And then, yeah, as far as the root, I don't think they ever it's impossible to test for root. We'd have to test for like empty string. I guess, yeah, if you test for empty string, that would work. But I think in these parameters, that never happens. So if you did want your thing to figure out like how many actual words are in here, then you would also increment the prefixes and the words for root. But I'm not going to do that, because it would only matter for empty strings, essentially. Okay, so we are making a new node, and then now we need to traverse into it. So we're going to say node equals node.children char, So now that we added this letter, we're going to add the prefixes to this letter. So we're going to add one to the prefixes. We're going to say no.prefixes plus equals 1. All right, and we keep doing that until we put in every single character. And then whatever is the last character, now we're going to take that trie and we're just going to increment that word count for that trie. So we're going to say no.words plus equals 1. So essentially we are just inserting new tries whenever we need to, and then we are incrementing this whenever it's the end of a word. So count words equal to, like all these are going to be very similar, so I'm just going to copy this and modify a little bit. So node is going to be self. This will never happen because I think they do say that, actually, no, I think this can happen. Yeah, this can definitely happen. So if character not in node.children, we should just return 0 because essentially we couldn't traverse all the way down, right? Yeah, so if character not node.children, otherwise let's just traverse. We don't need to add these things. And then if we were able to traverse down, to the final trie, that means there should be at least one node there. Should there? No, not necessarily actually. Because, yeah, not necessarily, right? Like, let's say we inserted, like, baller, and then we look for ball. It should still be 0, but it'll be able to traverse. So essentially, now what we need to do is we need to return. We are at the trie we want to be at. Now we need to just return the number of words at that trie, meaning that's how many words there are that are equal to this word. So we just return no.words, right? And in the first try problem, instead of returning no.words, you would just return this Boolean value, like, is this a word or not? But now we actually have a count. Okay, node starting with, all the same, right? So literally all the same. But now instead of returning no.words, you just return no.prefixes. Because, once again, if you have, a word like, let's say your try has baller in it, and you look for ball, you're going to be at the node after this try, and that will have a prefix, right? Because anytime we insert a word, every letter we get to, we will increment the prefixes. So, yeah, that's all the same. Now for this erase is going to be the only kind of like weird one. So we're going to make a node again, and we're also going to make a child, because when we traverse in a dictionary, right, like when we get a value from a key, we want to still have access to like that dictionary for the node, right? So if we go back to the picture, let's say we traverse down here, kind of like a tree relationship. If we traverse down to this child, we also want to have access to the parent, because if the prefixes for the child is 0, we want to make this cut, and you can't do that without having the parent. So we're going to store the parent and the child, and then we're just going to like update the child as we go. Okay, so we're going to make the child equals none first. Okay, so now we're going to do the same thing for character and word, or similar anyway. So child equals no.children char. And they did say that at least one of these will exist, so we don't have to worry about like this path not being valid or something. So we're going to say child.prefixes minus equals 1. And remember, if child prefixes become 0, then this try should just be deleted from the dictionary of the one above it, because that means that this child and everything in it should have a prefix of 0. And like I said, we're actually going to be deleting the nodes, not just changing values to 0, because that'll save us a little bit of space. Well, in Big O it won't, but in reality, this is like better practice, right? You want to delete things that you're not using. It's kind of like, let's say you have an array of elements, and instead of actually deleting them, you just change like the valid indices of an array. Like you'd still rather delete them from memory, right? So it's the same kind of thing. Okay, so if child prefixes equals 0, that means we want to be deleting this like child try. So if that's the case, we're actually going to delete no.children char. And we don't need to return anything, right? So essentially the way this erase is going to get tested is it will call erase, and then it will like call find word or something on this word, and this shouldn't exist. Okay, so we're going to be deleting, and then we're going to be returning, right? So if we delete this try, that means like let's say we're traversing down, and we delete this try. Well, if we delete this try, we delete all of its subchildren, so then we should not be like going down further because there's nothing there. Okay. So we're going to be doing that. We're going to be returning, and then otherwise we're going to update our node to be the child now. and then we're gonna, get a new child and so on. Okay. And then what we need to do is we need to actually decrement the words. Like let's say we went through this whole thing. Whatever node we end up at, we need to decrement the words, right? And so I'm trying to think of, do we want to decrement prefixes and words? I don't think so. I think just decrementing words is fine, because I think if prefixes goes to 0 and it's the last node, it will always be deleted. So like in this picture, if this is actually the last node in a trie, then the prefixes should always be equal to the words, because there's nothing like past it, right? So the prefixes would be like 1 here and 1 here. So when this gets decremented to 0, this will already get deleted. So if this words goes to 0, that means this can't be the this can't be the last node in the trie. Otherwise, it would have gotten deleted already. We would have handled that situation. Okay. So now we just say node dot words equals 0. Or not 0. Minus equals 1. Right. We're just subtracting 1. Okay. So let's give that a go. Oh, this is prefix. Okay. Let's see. Yeah, looks like it's accepted. Oh, yeah, I didn't even run the test case. So test case is fine. This is fine. Yeah, and this is reasonably efficient. Yeah, I think it is a little bit faster if you don't actually delete the nodes, because I think the way they test it is like, not sure. I think it does run faster in LeetCode if you don't actually delete the nodes, but in like a real, if you actually have to build a trie, right, it would be better to delete the nodes because you're saving memory long term. Yeah. So let's talk about the time and space for like all this stuff, I guess. So let's talk about one at a time, right? So for insert, that's going to be like O of the word. So whatever the word length is, right? Like worst case scenario, we're going to be inserting the whole word in here. So we're going to, like worst case scenario, all of these would be new tries, which would just be the length of the word. Count words equal to, worst case scenario, we're going to traverse down the whole length of the word. So that'll also be so equal to, and prefixes will be the same time complexity. You're essentially, it's going to be O of the length of the word. Worst case, you're traversing down the entire word. Best case, you short circuit somewhere because part of it's not in the trie. And erase, yeah, also the length of the word, right? So worst case, you go down the entire word. Best case, you short circuit somewhere because the prefixes become 0, and then you just delete like all the subchildren, and you don't have to go down the length of the word. Okay. Now we can copy this. And look for the space. So for the space, for insert, it would be the length of the word again, right? We'd have to make tries equal to the length of the word, essentially. Worst case. Count word is equal to would be O of 1. We're not really like adding anything. We're just traversing. Count word starting with would also be O of 1. And then erase would also be O of 1. Yeah, so all of these are O of 1 because we're not like adding, we're just deleting or traversing. And then insert would be O of the word, length of the word. Yeah, so I think that's going to do it for this problem. I don't want to get this red thing interesting. Okay, yeah, that's going to do it for this problem. So hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I will see you in the next one. Thanks for watching.